Hi everyone. In this video, we're going to continue on with our discussion of probability. And so where we ended last time, in the last video, we were talking about how to calculate probabilities or certain probabilities when you have two events and they are disjoint, or the two outcomes and these outcomes are disjoint. And what disjoint meant is that the two events could not happen at the same time. If one happened, the other can't happen. So there's no way for them to happen at the same time. Now, and so we learned a special rule about how probability works, or how to combine things in a sense, if the two events are disjoint. But what if they aren't disjoint? And so that means, if they are not disjoint, that means that if I have two events, that they can possibly happen at the same time. And so how do I deal with probabilities and combining them and adding them or subtracting them or all of these things if the two events aren't disjoint? And so for my example here, I'm going to use a standard deck of playing cards. And so if you know what that is, then you know what I'm going to talk about. But if you don't, then you might be left in the dark. So a standard deck of playing cards has 52 cards in it. So 52 cards, and each card has something different on it. And I've put all 52 outcomes here. So some are red and some are black. Half of them are red and half of them are black. And then they split up into four different what we'll call suits. Clubs, hearts, diamonds, and spades. So if you go row by row here, it is club is the first row, diamond is the second row, heart is the third row, and spades are the last row. Okay, and so you refer to a card as the value and then the suit. So the two of clubs is the very first thing in the top left of this table-ish thing, and each suit has 13 cards in it. And you start with the lowest number is 2, and you are 2 through 10, and then there's Jack, Queen, King, and Ace. So J stands for Jack, Q stands for Queen, K stands for King, and A stands for an Ace. Okay, and so this is what we're going to use for at least this example. Okay, and so now each card is equally likely to be picked if I picked one card out of a deck. Okay, and so what's the probability that a randomly selected card is a diamond? And then I ask three questions. So a diamond, a face card, and then a diamond or a face card. Okay, and so each of these have different varying levels of complexity. Okay, and so what's the probability that I randomly select a card and it is a diamond? Okay, well, there are a number of different ways that you can think about this, but I would think about it as how many cards are possible. So how many cards in the deck are there? There are 52. That's going to be the denominator of our probability. That's the size of our sample space. So in essence, the picture is our sample space. The size of the sample space is 15. And then how many cards are diamonds? So I told you that there are 13 of each suit, and so there are 4 suits. 4 times 13 is 52. Yeah. So how many diamonds are there? There are 13. I'm sorry. Excuse me. So there are 13 diamonds, 52 cards total, and so the probability of that card being a diamond is 13 divided by 52, or 1 divided by 4. You could also reason it as there are 4 suits, and I'm choosing one of them, so 1/4. That, of course, only works if there are the same number of cards in each suit. So anyway, if we go by what we've known so far, there are 52 cards, 13 of them are diamonds, so it's 13 divided by 52, and that would be our first one. Let's see if I do this. Yeah, sorry. So a diamond, 13 out of 52. What about a face card? So a face is a jack, a queen, a king, or an ace. Okay. So again, there are 52 cards in the deck. So that's our denominator. That's the size of the sample space. The size of the event a face card, well, you've got to count up the face cards. There are 4 suits. Each of them has 4. So it's 16 out of 52. 16 out of 52, which does simplify, but I don't know what 2 at the moment. Okay. And then a diamond or a face card. A diamond or a face card. We asked this question, this or question before, when we had disjoint events, and if the 2 events, the diamond and face card, were disjoint, we could simply just add the 2 probabilities that we found before. 13 out of 52 plus 16 out of 52. But that's not the case here, because there is such a thing as a diamond and a face card. The jack, the queen, the king, and the ace are all face cards and diamonds. So we have events that aren't disjoint, diamond and face card. And so what do we do to find that probability? Well, I have a Venn diagram here that I think will help us a little bit. So how many of there were diamonds? So in this Venn diagram, the blue represents and we're not I was incorrect in my calculation for a face card. The ace does not have a face. Sorry, it's been too long since I've looked at cards. Okay, the ace is not a face. So how many face cards are there? 3 of them per suit. There are 4 suits, so there are 12. And so the answer to number 2 would be 12 out of 52, not 13. Again, my apologies. And so the blue circle on the left-hand side of the Venn diagram, those are diamonds. The yellow circle on the right-hand side, face cards. And then the middle, which is green, are the face cards who are also diamonds. So there are 10 diamonds who are not face cards. There are 9 face cards which aren't diamonds, but then there are 3 of them in the middle that are both. And so how you're going to solve this is by doing what you would do when the cards are disjoint. So it would be the probability that the selected card is a diamond, which was 13 out of 52. That's one number. You would add the probability that it's a face card, which was 12 out of 52, okay, or 23%. But what we did here, that we what we did in so far, if we just added the 2 numbers, it would be incorrect, because we've double counted. We've counted those cards, those 3 cards in the middle that were diamonds and face cards. We counted them twice because they got included with the diamonds, but they also got included with the face cards. And so we only want to count them once for diamond or face card. And so for that third question, what you want to do is you want to add the 13 out of 52, or that's 0.25, okay, plus the probability that it's face card, 12 out of 52, which is 0.2308. You'd add those numbers together, okay, in which you'd get 0.4808. Okay, and then you subtract away those. You subtract away the probability of it being a diamond and a face card, which is 3 out of 52, or that 0.0577. Yeah? Okay. And so this is the rule that we would use, okay, what I was describing before. So this works for disjoint events and not disjoint events. This is the general addition rule. So the probability of A or B happening is the probability that A happens plus the probability that B happens minus the probability that both of them happen. And that is to get rid of that double counting. Now you'd say, why would this work for disjoint events? And it would work for disjoint events because the probability of A and B happening together for disjoint events is 0, and this formula simplifies to what we saw before for disjoint events. Okay, so another rule that we're going to use a lot in probability is the complement. And it's not probability being nice to you. So it is not a complement like that. It is this. So the complement. So for some event A, the complement of an event A, and I denote that. So before we get to the denoted part. So for some event A, the complement of A represents everything not in A. So it's actually the opposite of A. So for some event A, the complement of A represents everything not in A. And I denote that A raised to the C power. Okay, A, and then in the superscript, which is above A, it's A raised to the C power. Now, A and C are not numbers, and so I'm not raising a number to another power in this case. Okay, that's just how it's denoted. And so the formula that we have to work with, if A is the opposite of, if A complement, or the complement of A, I'll often refer to it as A complement. A complement represents everything that's not in A. So if I wanted to find the probability that A happens, I can actually, but that for some reason is really tiresome or troubling, or maybe I don't have that information. I can find that, or I can do that with the complement of A. And so the probability of A happening is 1 minus the probability of A complement happening. Okay? And that formula, if you think about it, should make sense, because you're either in A or you're not in A. So A complement represents everything else that is not A. And so that encompasses all of what could happen. So either you're in A or you're not in A. And all of that together represents the entire sample space. Okay? And the probability of the entire sample space is 1. Of selecting anything from the entire sample space, it's 1. And so that's how this formula is, or this equation was formed. Okay, sorry. Complement. Okay? And so you can reformulate the question, or reformulate the formula, the equation, to make it make sense, or use it in a different form. If you add over a complement, you get the thing on the left. So the probability of A plus a complement is equal to 1. That's what we were saying earlier. Or the one that I wrote. The one that I wrote. Okay. Now, we will use that complement rule a lot, and so you'll see it a lot as we work through things. Now, we've briefly talked about independence in the context of variables before, so we talked about independence back in chapter 1. We can also talk about random processes being independent as well. That's these variables that we've been talking about, or events, I should say, or outcomes, okay, which are random processes. Meaning I don't know what's going to happen before it happens. Okay, we can talk about those being independent as well. Okay, and so what does that mean? And also, this isn't the last time we'll talk about independence. This concept of independence comes up all the time, and we'll see it a lot even later on in the course. So, two processes are independent if knowing the outcome of one provides no useful information about the outcome of the other. Okay, so knowing the outcome of one provides no useful information or does not affect the other. And that's the same general definition of what I talked about of independence before, but it means, or we're going to work with it in a different way here. And so we're going to talk about it in terms of rolling a die or doing various things. Now, before I get to an example, the biggest part, what people get tripped up on a lot, is the difference between independent and disjoint or mutually exclusive. So that was in the last video, but we did talk about it a little bit in this one. Disjoint events mean that if one happens, the other can't happen. They don't happen at the same time. Independence means one does not affect the other. Those two sound similar, but they're actually quite different. In fact, they're really opposite. Disjoint is actually the strongest form of dependence you can ever have, because if two events are dependent or mutually exclusive, I'm sorry, disjoint, not dependent. Disjoint, they can't happen at the same time. And if they can't happen at the same time, if one happens, I know the other cannot happen, which is like the exact opposite of independence. It is very dependent. A is dependent on B because if A happens, then B can't happen. Okay, so anyway, there's a big difference between independence and disjoint / mutually exclusive. And so don't think they're the same thing. They're actually quite opposite. So, example, you're rolling 2 dice and you're interested in knowing the probability that both will land on 1. So what's the probability that the first dice will land on 1 and the second dice will land on 1? Okay, and so the question becomes, does rolling a 1 on the first dice roll, affect the probability of the second dice roll? So, does rolling a 1 on the first dice roll have any effect on if you're going to roll a 1 on the second dice roll? And the answer is no. The answer is no. And it looks like this. Oh, I'm sorry. It looks like this. So hopefully this diagram here will make it make sense a little bit more. And so what happens, or what we're looking for in independence, probabilistically, in a probability sense, is that the proportion. So you can think of the entire rectangle as the entire situation. So rolling the 2 die and looking at the outcome. Okay, and so if you look at the columns, so if you sort of think of this as a table-like thing, and you look at the column, so there's one blue column. Okay, the first blue column is, the first column is white, seemingly, and then there's a second column which seems to be blue. And so apparently the second column, however they fill this picture in, are the 1s. And so what's the probability that you roll a die and it is 1? The answer should be 1/6. Okay? And so the blue rectangle here takes up 1/6 of the entire rectangle. So the blue rectangle takes up the entire 1/6 of the entire rectangle. Okay, so that's a 1/6 on the first roll, and then we have the green rectangle inside of the blue, inside of the white. Okay, so a lot of rectangles going on, but in the green rectangle, that represents the times, or the 1 out of 6 times, so 1/6 time that you roll the first die and you get a 1, and you roll a second die and you get a 1. So it's the probability of rolling the first die and getting a 1, and then the probability of rolling the second die and also getting a 1. Okay, and so we don't actually know, we approximately know that the green rectangle is 1/36 of the entire white rectangle. Okay, so you could count that. In fact, I asked you to count that previously, of writing out all of the possible outcomes of rolling 2 die. And I could ask, what's the probability of getting a 1 and a 1? Okay, and you would say 1 out of 36. Now, it turns out that the green solid rectangle is 1/36 of the entire white rectangle. But what's important is that the green rectangle represents 1/6 of the entire blue rectangle. And that's the important part of independence. If 2 events are independent, then you're always going to have this situation where the proportion of area of the entire rectangle, the blue one, that the blue one is 1/6 of the entire rectangle, and then the green one is going to be 1/6 of the inner blue rectangle. Okay? If they aren't the same, then the events aren't independent. Okay, I know that was a lot. Okay? And it's not life or death if you don't understand that concept, but I thought I'd show it to you anyway. Now, what's nice, what you do need to remember, is that if events are independent, if I have two events and they're independent, the probability that they happen together, so the probability that A happens and that B happens, is equal to the probability that A happens times the probability that B happens. So you get this nice multiplication rule for independent events or independent processes, like it says here. And that extends to more than two events. It extends to as many events as you want. Okay? And that's what the second part does. If the events aren't independent, then this will not work, and you have to do something more complicated. But if the events are independent, that helps us, makes it easier on us to find these events, or find the probability that various thing happens about the events. So, I have your turn to end the video. About 9% of people in at least the United States are left-handed. Okay, so about 9% of people are left-handed. Suppose that I select 5 people at random. Okay, 5 people from a crowd. You can think of it as a simple random sample, but the type of sampling does not matter here. So don't overthink that. Okay. But I sampled 9 people. In essence, I rolled 9 dice, or did these random things five times. Sorry. So 5 people. What's the probability that all 5 are right-handed? What's the probability that all 5 are left-handed? And then what's the probability that not all of the people are right-handed? Okay, so hints for each of them. For number 1 and number 2, you're going to want to use the fact that if I talk to 2 people, 5 or 2 or whatever, if I look at these 5 people, you ask yourself the question, does the first person being left-handed affect whether the next person is left-handed, or whether the next person is left-handed? And your answer should be no. So it does not affect it. These are independent random processes. So you should use the independence fact and the multiplication rule that we learned last time to answer 1 and 2. And then for question number 3, you should use the complement rule along with your answers for maybe 1 or 2 to help you find the question to answer 3. Not all of the people. So that means, well, I'll let you figure out what that means. Okay? So that's where we're going to end, and I'll see you on Wednesday.